let's talk a little bit more about upper bounds and lower bounds and what they're good for. Okay, the big O notation gives an upper bound. Upper bounds are useful when you want to prove that something is okay. So let's say I'm traveling from between two cities by car, and I can prove that the upper bound of gasoline consumption is 100 liters. Now, if my gas tank is at least 100 liters, I am guaranteed that if I fill it, I will have enough gas. So I have proven that things are okay. That's the use of an upper bound. But sometimes we want to do kind of the opposite. We want to prove that things are not okay. So this is where the lower bound comes in. So let's say I'm traveling again between two cities, and I prove that I will need at least 50 liters of gas to do it. If my gas tank is only 40 liters big, then I can prove that if I don't fill it up during the trip, I will not be able to make the trip. So the lower bound lets you prove that things are not okay. And sometimes we want to do both. So sometimes we want to have both a lower and an upper bound. So big O only gives you an upper bound. So sometimes we want to have a lower bound. So we define the lower bound operation, which is called big omega. And we have another one which is both upper and lower, which is called the big theta. Now let's see how we define them. In fact, they're very easy to define. We've already done the hard work. The hard work is the definition of the big O. So big omega and big theta are easy once you know big O. So big omega denotes the lower bound. So F is big omega of G if and only if G is O of F. So if F is an upper bound to G, then G is a lower bound to F. Okay, so n cubed is omega of n squared. That means n cubed is always above n squared, since n squared is always below n cubed. The other one is the upper and lower bound. That's big theta. So we have that F and G are both bounds for each other, and that's a situation called asymptotic equivalence. So F is big theta of G if it's both big O and big omega of G. So if we have F here, we know that it's going to be bound below by G, but also above by G. So the F and G never really get very far apart. So with that, we have the different possibilities. Big O for upper bounds, big omega for lower, and big theta for both. Let me now give an example of the difference between big O and big theta. Theta, the one where we have both upper and lower bounds, where F and G never get far apart. So let's use our trusty first negative function, which returns the position of the first negative element. Now assume the list L has a size n. Let's take a look first at the worst case time. So we have to choose the list inputs that give us worst case. So we're going to choose only lists where all the elements are positive except for the last one, which is negative. In that case, for all of those lists, the time will be proportional to n. So the worst case will be theta n. It's always proportional to n, never more, never less. Now let's take a look at the average case, F average. Now, what inputs are we considering? We're looking at all possible lists. They might have different probabilities, but assume that all the possible lists are possible inputs. In that case, some of those lists will be very fast, order 1, constant. Some will be slow, order n. But they're all bounded above by n. So the average time complexity is O n. Okay? That means for some inputs, it actually might reach that, or maybe it doesn't. Maybe for all lists it's very, very small. But it might, in the worst case, maybe reach n for some inputs, but in any case it's always going to be less than n. But in theta, they're always going to reach that point. They're never going to be less.